Welcome back. This is the continuation of the previous lecture. In this lecture, we are going to prototype and we are going to show how a Verilog HDL programming and FPGA prototyping with hardware experiment of PWM PSM multimode digital control. So, here we are going to revisit our PWM PSM multimode digital control technique, then Verilog HDL synthesis of voltage based multimode digital control, and then assessment of transient performance using experimental result. So, if you recall our last lecture, previous lecture, where we have discussed about these modules in the context of digital multimode digital PWM PSM control. So, here we are taking the A to D converter, that is the voltage loop, and we are generating the gate signals and all this discussion, and this is the option for mode selection. If it is 0, it will throughout take the DPWM. If it is 1, then at high load we are setting PWM, and light load we are going to pulse skipping modulation. Now, in this architecture we are building the main module. So, the main module, if you see, this is the main module, and this main module name is here. This is the name of the main module. Now, what we are going to see, we want to map all the input output pin. That means, if you see the ADC data, so this is our ADC data. Okay. So, if we take once more the ADC data, this is our ADC data. Next, we want to show what is the ADC clock. So, this is the ADC clock. Okay. Then, what is the main clock? So, the main clock is here. The main clock is here. Okay. Then, Q transient, we are not giving this option here. We are setting that because this was set for load and reference transient, but since we are taking only load transient, so this option for this particular case we are not considering. Then what else? Then we are talking about this Q load, the option, mode option. So, this is the option, mode option. Then PWM high, PWM high is okay. Let me go in the other path. PWM high we can take from here to here. Then PWM low, so this will go from here to here. Then ADC data we have already shown. Q load, this is the Q load. Okay. So, that means now we have mapped all the input output which are external interface of this main module and which are going to the FPGA different pins. Okay. Now, we have to define these are the scalar input and scalar output. So, these are all scalar, and this is the vector input Q1.9 sine format, and this is we are not using DAC. So, these are wires, all this definition. Now, what are we going to do? Here we are taking the output voltage, and we have discussed that whatever ADC data is coming, we have discussed multiple times. So, this is our ADC data, this is the register, and we have a clock, that is our switching frequency clock, or here we are calling as a PWM clock. You can say this is the PWM clock, this is you can say FPWM, and data which is going out is my N out, that means the output, and this data was subtracted from the reference command which is nref, and it is generating the error any which is here. So, this is the error, this we are discussing, and this is what we are talking about, this reference minus out. Now, the controller output, that means since we are going to use DPWM and we will discuss. So, this structure, that means what we are going to do if we consider this N con. Okay, so, let me take a different color which is our N con. This is going to our DPWM block, So, in case of PWM, this N con will be the output of the controller. In case of pulse skipping during charge pulse, we are giving a fixed duty ratio. Okay. And we need a high frequency clock, and this DPWM also we are taking PWM clock because we want to reset this counter based on the age of this clock, and the output of this is coming to be Q out, that we will discuss. And this N con for this picture, it is clear that it is the output of a mux 0 and 1, where this one is the N con PSM, N con PWM, that means output of a PWM controller, and this is the N con PSM. Okay. And what is the select line? The select line here, if we use a different color, so select line here is this one. That means, if the select line is 0, it will take PWM. If the select line is 1, it will take this NPSM. So, this is going to digital. Now, we are instantiating the clock generator circuit, digital PID controller, counter based DPWM and the mode selection. So, I have just shown the overview of this counter based DPWM, but the mode selection will decide what output should be taken. Is it the output of the, because it will generate, finally we are generating this PWM PSM flag signal from a transient detection circuit. But actual commercial product, whether to select PWM or PSM, that depends on some transient detection, some load estimation. There are n number of algorithms, but here we are making it simple just for understanding, that we are assuming the load transient comment we are sending from our digital control platform by turning on and off the switch resistance, and we know the transient. So, whenever it is going to load transient high load, it is directly moving into PWM. When it is going to light load, then we are essentially operating the converter under PWM for few cycle and then moving to PSM, and we will explain why we are doing that. So, this is the overall diagram, and then module for clock generation, that we have discussed in lecture number 72 in detail. So, I am not going to repeat this block, these are all standard and we have already discussed. Only thing, we are not generating a DAC because we do not need a DAC clock. Otherwise, whenever we need a current mode control based architecture where we need to use DAC, we are using essentially the identical clock of ADC, but it is flexible and it can be programmed. Now, the digital PID controller, this also we have discussed in lecture number 73, where we have developed the Verilog HDL code for the digital PID controller. Everything else is same, except we are considering an additional reset circuit, and this reset logic is that if this is 1, then I will say integral action disable, and if it is 0, that integral action enable with reset condition. That means integral action disable means it is reset, basically it is set to 0. Whenever it is starting integral action, then the initial value will 0 and then it will keep on adding, and this will also have some problem, particularly when you make for PSM to PWM. I will discuss that, but during the pulse skipping operation, why we are resetting the integral action? Because the PWM integral action will actually accumulate all the error, but under PSM, since the average output voltage is always above the reference voltage, because as per the pulse skipping logic, if the output voltage just fall below Vref, then the charge pulse start, and then the voltage goes above the Vref and then it starts discharging. So, all the time the output voltage is more or less above Vref, and if we enable the reset integral action, then the error will be negative all the time, because it is error voltage will be, we know error is what? It is Vref minus V0. Since V0 will be always above Vref, error, so this negative quantity will be accumulated and this can cause some wind up problem, and also during transition the controller output will be very much negative. So, you want to avoid that. Other than that, this PID controller, everything we discussed in lecture number 73, and we have used here Q6.13, there we have used Q4.15, but again if we understand all these Q formatting properly, then there is absolutely no problem. So, this the resizing the data, and then finally we are generating the controller, and here you will find the output of the integral, which is this one. If you see this block, the integral controller output will be 0 if the I reset is enabled, otherwise it will take the regular integral action, and that is what I have discussed. So, when the reset will be high, then integral will be disabled and it will be set to 0, the output of the integral. Now, we are also using a counter based DPWM, because I have shown some overall diagram, and we have discussed this counter based DPWM, we have discussed in lecture number 69 and 70, but here that means the counter based DPWM will take a count output. That means this logic, simply the slight difference here is that in this logic I will say it is the counter base DPWM. Input to this block is here, as per this it is like controller output, but this controller output can be either, this is just a definition, local variable, and if you go for the module instantiation block, you will find that this count PWM, the local variable is the ncon. That means this particular controller output in the bigger in the broad sense, yeah. So, in the broad sense, this controller output, it is a local variable inside this block, but it is actually this thing 0, and so inside this module, I would say inside this module its name is this, but we are connecting locally. So, this name is ncon. That means this is just an interface, that means the same data, outside name is ncon, inside, that is in the main module, and which is interface or wire connected, inside name is control output. And what is this? So, this is your ncon PWM and this is your ncon PSM, and there is a flag which is your FPWM PSM. That means if the flag is 0, that means if it is 0, then this get connected to this, and this is coming out from GCZ, the controller output, and input is our error voltage. That means the controller output will be connected if it is operating under PWM, but if it is 1, that means if it is 1, that means it will get connected here if it is 1, and in that case it is PSM, and in PSM we are applying a fixed duty ratio. So, it will be a fixed number, it is a fixed number in this, okay, and that we have parameterized at the very beginning. If you go to the main module before that, so this is the ncon PSM, and this is, you have to match, that means it is totally 14-bit data, the ncon which is the controller output, which is going to the this data, it is a 14-bit sign in Q6.8 format. So, accordingly NPSM is set, and this is set to have 30% duty ratio. That means during on time we are giving 30% duty ratio during the charge pulse. Okay. Now, this counter output, so then counter also require for incrementing, it require, we are using a PWM clock edge, because it is taking the PWM clock edge. Sorry, counter is incremented with the high frequency clock, which is our F clock, that is the high frequency clock. So, this is the clock. which is used. And it also uses a reset, the counter is reset. For that we are using this clock. This clock we are using as a reset, that means reset is our FPWM. And this is my output of this, that is output. Okay. So, here it is taking a sign, and we have discussed the basic operation of counter DPWM, counter based DPWM in lecture number 69 and 70. So, I am not going to repeat this, it is already discussed in lecture 69 and 70. Now, the next part, which is one of the very crucial part, is the mode selection. So, how are you going to select mode? First of all, there are two modes. One is because DPWM mode, another is a DPSM, that means digital PSM. So, whether you call it a digital PSM or PSM, maybe we can use a generic name, because it is a PWM we are implementing digitally, but basically this is a PSM. So, PWM we are defining. Under PSM, what is there? So, PSM, what it will do? It will take, I would say, error. That means we have the error voltage, which is N ref minus N out. Now, it is a Q 1.9 sign forward, and so the 10th bit, basically the MSB, okay, I would say it has totally 10 bit. The MSB indicates the sign bit. So, if we take NE9, if this is high, then what does it mean? That means as if we are setting it like this. If this bit is 0, then at the edge of PWM clock, this counter, which is your D flip flop, it is your QPSM. That means, if, what does it mean? At the edge of this clock, that means at the edge of this clock, if this is low, that means if NE9 is equal to 0, what does it mean? This implies, or I would say 0 means your N output, N out is less than equal to N ref, and if it is 0, then its invert logic will be 1 and then QPSM will be 1, which means if the output voltage, this implies that output voltage is less than Vref. So, at the edge of this clock, if it says the output voltage is less than equal to Vref, then the cycle will be charged, that means QPSM will be 1. So, you need to charge the inductor, that means the switch should be turned on, and the duration of the on time will be decided by the width of the fixed width, which is set by the N con PSM. But if this guy is 1, if this guy is 1, then this invert will be 0, then QPSM will be 0. Then actual gate signal, that means you can say, so there will be another logic. I mean, if you go to the next one, that is here the Q gate PSM, Q gate PSM, that is your QPSM multiplied by the Q, that means your Q what, the output of the DPWM, that is, so we are setting Q out, that is the output of the PS, output, this is the output of DPWM block, okay, and this we are setting as Q gate PSM. That means this will be the gate signal, main gate signal during PSM. But we have the choice whether to set the PSM or we need to select the PWM. That means now in addition to that, So, this is 1, this is 0, and it will simply take Q out, and which will be your actual Q gate I will say, and this is your FPWM PSM, the mode logic. That means, if it is set to 0, it will take Q out, which is the output of the DPWM. In that case, the input to the DPWM will be output of the controller, N con PWM. But if this is high, then it will set the PSM logic, and in that case the DPWM will be output will be ANDed with QPSM. QPSM will decide whether the cycle will be charged or skipped. If it is charged, it is 1 for the whole cycle. If it is 0, means it is skipped. And during that time, the Q output, which is the PWM output, will be decided by the input of the DPWM, which is the N con PSM. That is a fixed quantity. Okay. So, this is a mode selection logic, and accordingly the Q high that we have discussed and Q low. So, now we have one signal is that Q gate PSM that we have discussed, and that is muxing with that is 1 0, then Q I would say here, if you see, get QH temp, because you remember for DPWM, this is the DPWM, and output of the DPWM will also have a dead time circuit. Dead time circuit will have this Q high, and there will be another Q low, QL temp, because under PWM we will operate in a synchronous configuration, and this will be going to Q high side gate signal based on the select line. Now, there will be another option, again 1 0, this will be simply 0, this will go to Q low, this will go to Q low, this will go to the gate drive circuit, and for this all this flag here it is F PWM PSM. That is it. This is a logic that we are describing. So, now we are creating a transient. So, suppose when it was in high load, we know Q load is high, then we are operating in PWM. Suppose it goes to PSM, then we are simply setting to PSM, that means when it goes to light load. But you see, whenever it goes to light load, then if you consider the inductor, then this capacitor, suppose your resistance was there, which is a continuous resistance, which is a large value, and there is a switch resistance, and this is your QL switches. Now, when this QL initially was connected, so when it was connected, that means you can see this condition link with this. So, it was connected. This time it is disconnected. Now, since the total lead current will decrease because this low resistance path is removed, but inductor current was high. So, it has to, that means you have more current coming in from the inductor than the current going out of the capacitor. So, that means the effective capacitor current will become positive, large positive, because suddenly you have removed the load, and this will cause an overshoot. But inductor, so this overshoot can be, to get back the regulation point, you have to extract the excess charge from the capacitor, but if you purely operate in DCM, the inductor will hit 0 and it will remain 0, because there is no other path than this high resistance path, and it will take longer duration based on the amount of light load current, and this will cause a large recovery time or settling time when you are going for step down transient. So, to overcome that, actually you can operate PWM for a small time. That time the current will go negative because it is a synchronous converter, and it will extract the charge out of the capacitor, and by that way you can quickly come back to steady state, and then you can actually again move back to the DCM operation with pulse skipping, so that you can save the light load efficiency. And this is a standard practice, and we have also discussed this aspect for constant on time context in this paper. Now, this is the transient we are creating. So, you can see here there is something called N mode into T clock. So, this is the number of clock that we are turning it on PWM operation even after the load step down transient to extract the current, and that will decide how many. So, this is number 10 number of cycle we are operating in PWM, because we are not doing any large signal based control which could take 2-3 cycle to come back or 1 cycle, but here we are making small signal operation. That is why we are allowing for certain time and then we enable. So, this is what actually I told, that if the load current goes high, that means we are deciding the number of. So, total 100 cycles are given, 50 cycle load high, 50 cycle load low. This is based on this, and we are setting the load to be transient, but this signal we are allowing for some more time to turn on the PWM operation. So, this mode actually it is supposed to be, because your load is 0, that means it is light load, but we are still continuing for 10 more cycle in PWM, and then we come back to this mode to PSM. So, this is like a PSM, this is PWM, and then of course, this is PWM because it is under high load. When they are equal, this is PWM and this is your high load, that means this is your PWM and this is your high load, but this is your light load. This is also light load and this is also light load. So, for light load, for some cases we are using PWM. Okay. Now, we want to show the hardware implementation. So, this is a buck converter that we have demonstrated multiple times in this course, and now we have written the Verilog code, and we already know how to synthesize the Verilog code and plug into or dump it to FPGA, and we have followed the same step. We have considered our hardware prototype of 1.8 microhenry inductor, 200 microfarad capacitor. We are taking the test condition at 3.3 input voltage, output voltage is 1 volt. Switching frequency under PWM is fixed 200 kilohertz, but under pulse skipping it will vary because depending on the number of skip cycle. The load resistance, the fixed value is this, and there is one more which is 0.33 ohm, that is under high load. So, when this switch resistance will be connected, it will be high load, when it is disconnected, it is under light load. So, the additional we are using a ADC resolution of 9 bit, even though it is a 10 bit ADC, we are discarding 1 MSB to avoid any limit cycle oscillation. Feedback gain is 0.2, clock frequency is 100 megahertz. Now, we are showing experimental results. So, test condition, we are using the same Kp, Ki, Kd which we have discussed in week I think 11 in the design, where we have designed digital voltage mode control design. I think it could be lecture number, I think it is 104 to 105, something like that. So, here we have discussed this, or maybe 106, 102, 3, 4, 5, yeah. So, same value for 3.3. So, this is the step up transient, and you can see the undershoot here is roughly around 180 millivolt, and the overshoot is also around 180 millivolt, because it is a 200 millivolt scale, and this transient time you can see here, this is the scale is 100 microsecond. So, it is around 70 microsecond that we found, and here also if we take this transient time, here also we are getting around 70 microsecond. Now, this is when you are operating throughout DPWM, and you can see this is under very light load, but under light load we are still operating in synchronous configuration, right, synchronous buck mode. As a result, your losses will be very high because the switching frequency is very high under PWM. So, this is your DPWM for both these cases. So, here the light load efficiency will be penalized, it will degrade because the switching frequency is high, driver loss will be high, and you are unnecessarily burning power. Now, we are enabling multimode. So, you see here, from here you are actually PSM start, and you can see there is a large ripple, and here there are two charge pulses followed by multiple skip cycles. Okay, PSM mode. So, this operating region is PSM mode, and this mode to this mode is your PWM mode. Okay. So, high power is fine, but now you see we have told this we have taken 10 cycles. So, this we have operated under PWM just to improve this recovery time, because this time is also like around 60 to 70 microsecond. That means the step down transient remains same as earlier, but this actually has a problem. Now, this undershoot is coming like a 200 millivolt. Why? And the recovery time is also large. It is it is coming to be, if you take from here to here, it is 100 microsecond scale. So, it is like 140 microsecond, which is almost double. But why? Because I have discussed in PSM, your error voltage is generally negative, because your output voltage average value is generally greater than the average value Vref. So, as a result, integral, so we have disabled the integral. Even though we disable the integral, the Kp into Ve, that is the proportional gain at the time of this mode transition, it is negative. Derivative gain is also negative, because Kd into Ven minus 1, this is also negative. In fact, this condition when you turn on, this is basically 0, because error is settled. So, this will primarily drive during the mode transition, this will primarily drive, and this quantity is negative. I would say this is during this time, this quantity is negative. As a result, it is going down and switch is actually turned off for some time at the beginning, and that is taking down the current. So, to overcome that multimode, so if you zoom the step down transient, so we have retained, in fact, we got just like a 40 microsecond, even it is far, I mean very good, almost we can retain the PWM operation, and we have continued from here to here, we have continued 10 cycles, nearly 10 cycles in PWM, then go to PSM. And this logics actually product to product varies, there are different type of logic, but I am just showing conceptual understanding. Now, the multimode, if you step up, this is the problem I have explained, because initially instead of going up, it is going down. So, reverse direction due to negative effect from Kp I will not say negative effect, due to the negative value of error voltage at the point of transient. Okay, and as a result, this term become, so this term become negative. So, to overcome that, we added a feed forward term. That means, we have added some offset term for few, I mean at this time of transient, and this is continued. Since there is an integral action, it will take over. So, undershoot, now this undershoot remains the same as PWM, but settling time has increased, because the integral will take slow action to reach, but we can make the output voltage undershoot can be reduced. So, that is one of the most important part. That means, this feed forward term is an offset term, and that is the digital platform it will allow. So, any transient if you can detect and if you can add an offset term to quickly ramp up, that is possible. Now, we are showing the comparative study. This is purely DPWM, this is with multimode, where we suffered this operation, and you see this undershoot and this undershoot are same, they are same. This undershoot, these also are same. So, you can retain it, and we can now achieve very high efficiency also. And experimental transient with now because it is a multimode, we are now enabling the bifrequency operation. So, bifrequency operation, bifrequency DPWM we have discussed in lecture 111 and 112. So, if you go, there is a almost insignificant impact, and the transient, this is without bifrequency, and this is with bifrequency. So, you can reduce the spectral peak, and if the transient response, there is no change in the output voltage transient. So, by that way we can enable, because we have discussed the need for multimode in lecture number 90, in lecture number 100, where we have identified that in high power it is essential to have spectral spreading for EMI reduction, that can be achieved. We want to achieve fast transient, that also we have achieved. We want to reduce the undershoot overshoot, that is also achieved. So, now this multimode control, you can play with multiple features and make it super fast with highly efficient converter. And in this we have some work which is in the context of multimode that can be useful for pulse keeping control basically, and this can be also multimode constant on time, pulse keeping, and combination of PWM. So, all these things are discussed here. So, in summary, we have revisited our PWM PSM multimode digital control, Verilog HDL synthesis of voltage based multimode digital control. We have also made some assessment of transient performance using experimental result. Now, we will go in the next lecture the another multimode control, which is a peak current based constant on time adaptive multimode control, which is interface with the PWM fixed frequency peak current mode control. That is it for today. Thank you very much.